The next section we're going to take a look at today is about redox reactions. A redox reaction is a reaction where the element's charges change. The word comes from two reactions that are occurring simultaneously, a reduction reaction and an oxidation reaction. So reduction, oxidation that occur simultaneously are called redox reactions. There's a couple of different ways you can define oxidation and reduction. The original definition, the one that's sort of specific, is the gain of an oxygen. So like if you have magnesium plus oxygen to make MgO, that's classified as an oxidation reaction because magnesium has been oxidized. The converse of that for a reduction would be the loss of an oxygen. So if you had copper oxide plus hydrogen, and then you lost that oxygen from the copper to get copper by itself in water, that would be the loss of an oxygen. That's one way you can define a redox reaction. When you're dealing with organic chemistry, oxidation, reduction reactions, oxidation can be defined as the removal of a hydrogen from a compound, or for a redox part of that, the addition of a hydrogen to an organic compound. We're not really going to talk about that definition though. The one that we're going to sort of define in our section is oxidation is going to be the loss of electrons, reduction is going to be the gain of electrons. One way to remember this is through the acronym OIL-RIG, where O stands for oxidation, I stands for is, and L stands for lost. And then you have to remember that it means electrons. And then the RIG part means that reduction is the gaining of electrons. So if something loses electrons, it's being oxidized. If something is gaining electrons, it's being reduced. One other way to determine what's being oxidized and what's being reduced is by looking at the reactant versus product's oxidation number. If you increase the oxidation number, so for example, if you have magnesium and it goes from 0 to +2, it means that the oxidation number is increasing. That means magnesium is being oxidized. You can verify it with definition 3 because it's losing electrons in order to become +2. On the converse side, reduction is a decrease in oxidation number. So for example, if you had Cl -1 and it became Cl2, its oxidation number is going from -1 to 0. Actually, that's oxidation, my bad. Let me find a different one. A decrease in oxidation number would be like Cl2 to Cl -1. So your oxidation number is going from 0 to -1. So you are losing, you are going down in oxidation number. And it also means that you are gaining electrons, which checks out with the RIG part of OIL-RIG. Okay, so let's take a look at this equation right here. Remember that the oxidation number tells you how many electrons something has gained, lost, or shared. So if you have an element like you do with zinc, its oxidation number is 0. Okay. So the first thing that we should do is let's go ahead and write out the ionic equation. So zinc is a solid, so it's going to stay zinc solid. Copper is aqueous, so we're going to write it as Cu+2. Sulfate is SO4 2- AQ. Over here, we're going to have Zn+2 and SO4 2- AQ. Again, because it's aqueous, we're going to split them up into ions. And then copper solid. Our spectator is sulfate. The ionic equation is Zn solid plus Cu+2 AQ goes to Zn+2 AQ plus copper solid. Okay, so now that we have the ionic equation, let's take a look to see which element is being oxidized and which element is being reduced. Because zinc does not have an oxidation number, we say that its oxidation number is 0. If you are an element by itself, whether it's a single element or a diatomic element, its oxidation number is 0. Copper's oxidation number is simply what its superscript is. Zinc as well over here is +2, and here copper is a solid, so it does not have an oxidation number. So we see that zinc starts as 0 and it ends up as +2. It is increasing in oxidation number, so that tells me that zinc is going to be oxidized, okay, which means that it is losing electrons. It is losing 2 electrons to become +2. Remember, when you lose electrons, you become positive. When you gain electrons, you become negative. So zinc is losing 2 electrons to become -2. Where are those 2 electrons going? So zinc loses its 2 electrons. Simultaneously, this is where the redox part comes in. The copper, we'll see in a second, is going to gain those 2 electrons. So let me erase this so we have a little bit of room to write. The copper is going from +2 down to 0. So it's going from a higher number to lower number. So that means the copper is getting reduced, and it is going to gain 2 electrons, which it gets from the zinc. So it's sort of this symbiotic, beautiful relationship between the electrons that zinc loses and that the copper gains to create this redox reaction. Okay, so zinc has lost 2 electrons and copper has gained them. All right, let's take a look at this one. So let's go ahead and write the ionic equation first. We have Cl2 gas plus, we're going to go ahead and bring the 2 with us. So it'll be 2K positive plus 2I minus. That coefficient basically distributes to both the K and the I. Yields 2K positive AQ plus 2Cl minus AQ plus I2 solid. So our spectator ion is going to be the Ki, or the K, not the Ki, the K positive. And we don't have any other spectator ions. So I'm going to rewrite this as Cl2 gas plus 2I minus yields 2Cl minus AQ plus I2 solid. So go ahead and erase all this other stuff above it so we have a little bit more room. Okay, so now let's see what's being oxidized and what's being reduced. Chlorine is a diatomic elemental gas, so it's going to have an oxidation number of 0. Iodine is going to have an oxidation number of -1. Yes, I see that there is a 2 out there. That 2 does not affect the oxidation number when you are going to calculate which is being oxidized and reduced. Those oxidation numbers are solely dependent on just one. It means there's 2 of them, and it will have to balance, but you're not going to put -2. You're going to put whatever the oxidation number is for just a single I. Same thing over here. Chlorine has an oxidation number of -1, and this I has an oxidation number of 0. So let's take a look at the chlorine. The chlorine is going from 0 down to -1. This oxidation number is decreasing. So we say that chlorine is being reduced, which means that it is gaining electrons. Okay, where is it gaining electrons from? Probably the iodine. So iodine is going from -1 up to 0. So its oxidation number is increasing, so it is being oxidized, so it is losing electrons. Okay, so it's going to lose 2 electrons. Those 2 electrons are going to be picked up by the chlorine. So again, it has this sort of perfect relationship of the electrons lost by the I are going to be picked up by the chlorine to produce these products. So on a test, if it asked which element is being oxidized, the answer would be the I. which element is being reduced? The answer would be the Cl2. All right, let's take a look at this one. And because I think we can get good at this, I can see right away that the sulfate is going to be my spectator ion, so that will save me having to do an extra step. So we're going to write zinc plus Cu plus 2 Aq. If you don't know where that plus 2 came from, I did it in a quick step. If you don't know where that came from, go back and review writing ionic formulas. And over here, zinc plus 2 Aq plus Cu solid. Okay, so now we can look at oxidation numbers. So oxidation number of zinc is 0, copper is plus 2, zinc is plus 2, and copper on the right is 0. Zinc goes from 0 to plus 2. It's oxidizing. So it's going to lose 2 electrons to bring it up to plus 2. When you lose 2 electrons, you become positive. Those 2 electrons are going to be gained by copper. Copper goes from plus 2 down to 0. So it's being reduced, which means that it is, so it's sort of confusing because you're being reduced, but you're gaining electrons, so it's sort of hard to understand. It's gaining those 2 electrons from the zinc. I think we already did this one, so we're going to skip this one. Let's take a look at this one. This is an equation that is already written in its ionic form. So all we have to see is which one's being oxidized and which one's being reduced. Magnesium is a solid. It's not bonded with anything, so it has no oxidation number. Copper is going to be plus 2. This copper is going to be 0 because it's a solid, and this magnesium is going to be plus 2. So the magnesium is going from 0 to plus 2. It's being oxidized, which means it's going to lose 2 electrons. The copper is going from plus 2 down to 0, so it's being reduced, which means it's going to gain the 2 electrons that the magnesium lost. One other thing to add, a little vocabulary, is so now we have something called a reducing agent and an oxidizing agent. It's very easy, but a little confusing because it's opposite. The element that gets oxidized is magnesium. We call the magnesium, though, the reducing agent. So the reason it's the reducing agent is because when it gets oxidized and loses 2 electrons, it is responsible for reducing the copper and giving copper those 2 electrons. So whatever is being oxidized is called the reducing agent, and then whatever is being reduced, the copper 2 positive in this case, is what we call the oxidizing agent. So it's not confusing, it's just you have to remember that whatever is happening to it, it is the opposite agent. Okay, because it goes into making the other one either oxidize or reduce. All right, label if the following examples are being oxidized or reduced. So fluorine, it is elemental, it doesn't have an oxidation number, goes from 0 to 1, so it's being reduced. Iron goes from plus 3 down to 0, so it's being reduced. Iron plus 2 goes to plus 3, it's increasing, it's being oxidized. Chlorine is going from -1 to 0, so it is going up, so it's also being oxidized. Finding the oxidation numbers in a polyatomic or compound, the general rules is that oxygen is -2. So what's going to happen is you're going to have an equation, and what you're going to do is you're going to write the oxidation numbers above each of the elements or polyatomic ions to determine what's being oxidized and what's being reduced. So not writing out the entire ionic equation, you're just going to be given a normal equation, and you're going to have to do this sort of in one, like, less steps. Hydrogen is going to be +1. Alkali and alkaline earth metals are going to be +1 or +2. Alkalis are +1, alkaline earths are +2, and the halogens are going to be -1. Okay, this list of rules is sort of like order of importance. So if the higher up you are on the list, the more like predominant that rule is. So if you have an oxygen and you have a halogen, the oxygen rule that's -2 is more prevalent or predominant than the rules below it. Okay, because sometimes what happens is with the nonmetals, if you're not listed on this, sometimes their oxidation numbers can change, and so you're going to have to calculate what the oxidation number is on some of them um, based on these set rules and then based on a little bit of algebra. And let me show you what I mean there. All right, so we have CaCl2. So to determine the oxidation numbers on these, calcium is an alkaline earth, so it's going to have an oxidation number of +2. Chlorine is a halogen, so it's going to have an oxidation of -1. Now, one way to check to make sure you did this correctly is because calcium chloride is a neutral ionic compound, the charges have to add up to 0. So if you look at it, you have one calcium that has a +2 charge, and you have two chlorines that have a -2 charge. So they contribute a -2. That equals 0, as it should be. Okay, so all of these compounds, unless it's a polyatomic ion that has a charge, should add up to 0. Okay, so that is how you do that one. For CH4, hydrogen is on this list, so we do that one first. It has a +1 charge, and then I'll show you a little bit of algebra and how this works out. There's 4 of them, and they all contribute a +1 charge. The carbon usually is 4, but for these, because they are covalent compounds, can actually change. So you're going to call it X, where X represents the oxidation number of the carbon. That has to add up to 0. So 4 positive hydrogens, their charges, plus X equals 0. So X equals -4. So it means that carbon's oxidation number is going to be -4 in this case. So you have to do that little bit of algebra trick in order to calculate what it's usually a nonmetal, what the nonmetal's oxidation number is. All right, let's take a look at KNO3. So here, there are 3 elements, and you check to see if any of them are on that list up there, so you can fill those in first. And we see that potassium is an alkaline metal, so we're going to go ahead and say that's always going to be +1. Oxygen is on that list, so we're going to say oxygen has a -2 charge, and then so usually you could look at, so what people probably want to do is they're like, oh, nitrogen, I learned that nitrogen is in group 5, so it's going to have a -3 charge. But when you are dealing with polyatomic compounds or 2 nonmetals, that oxidation number actually can change. So those numbers that you learned for group 5, 6, and 7 are only if it's with a metal. Otherwise, you have to do this little trick. Okay, so what we're going to do is we're going to calculate what nitrogen's oxidation number will be in that compound. So we have 1 potassium that contributes a +1 charge, so we're going to go +1. We have nitrogen. There's 1 nitrogen, and we don't know what its oxidation number is, so we're going to call it X. And then we have 3 oxygens that each contribute a -2 charge, so it contributes a total of -6 to that overall molecule. And we want to say that that adds up to 0. So doing a little algebra, X minus 5 equals 0, X equals +5. So in order for this compound to work out, its oxidation number has to be +5. So if you were to try to do that -3 that we learned like a chapter or 2 ago, you would not have it correctly because, again, those were only if you had a metal and nonmetal. So it's a little bit different now. CO2, number 4. So oxygen is going to have a -2 charge. So what will carbon's oxidation number be? Well, we can call carbon's oxidation number X, There are 2 oxygens which contribute a -2 charge, so they contribute a -4 charge. You can write it one of 2 ways. I'll just show you. You can do plus -4 like I have been doing, or those of you guys who are good at 5th grade math know that that can be simplified to x minus 4 equals 0. So carbon is going to be plus 4 in this case. So another thing to note is that here carbon is plus 4, here carbon was -4. So this is sort of why you have to go through these steps to do this. All right, let's take a look at number 5. So chlorine is on this list, so we're going to say that it's a -1. And then in order for the iron to balance with the chlorines, iron has to have a +2 charge. So +2 iron plus -2 from the chlorine adds up to the neutral 0. Na2SO3, we have 3 elements. Oxygen always is -2. Sodium, which is an alkali metal, is going to be +1. So what we need to do is find the oxidation number of sulfur. So here we have 2 sodiums, which each contribute a +1 charge. We have sulfur, which we don't know, we'll call X. And then we have 3 oxygens, which each contribute a -2 charge to add up to 0. So we have X, that's -6 plus 2, which is -4 equals 0. Therefore, the oxidation number of sulfur is going to be +4. This is going to be +4. Now, the reason we're doing this, like why are we going back and doing all this silly math? The reason we're doing this is because these elements, or compounds rather, are going to be put into an equation, and then you have to determine what's being oxidized and what's being reduced. That's why we have to kind of interject and do this little lesson so we can move on to the next part. Oxidation numbers for charged particles. The charges on each element has to equal the charge of the ion. So if you have a polyatomic ion, you're going to do the same thing as we were doing in the previous slide. But instead of adding up to 0 in the previous slide, for a polyatomic, it has to add up to the overall charge on the polyatomic ion. So for example, sulfur, which we don't know, we'll call X, has a charge of X, and then oxygen, which has a charge of -2, means that 4 of them contribute a -8 charge. Those charges, instead of adding up to 0 now, because that ion has an overall charge of -2, has to add up to -2. So this time, X is going to equal to +6. So sulfur will be +6. Okay, so let's take a look at NO3 - 1. Oxygen is going to be -2. Nitrogen, we don't know, we're going to call X. 3 oxygens that contribute a -2 charge will be -6. And here, because there is a charge on the ion, has to add up to that charge. Therefore, X equals +5. So nitrogen's oxidation number is +5. MnO4 1-, oxygen is -2. Magnesium we need to calculate. We'll call it X. X minus 8. The 8 comes from 4 -2 charges. It has to add up to -1. X equals +7. Here, PO4 3-, oxygen has a -2 charge. Phosphorus we'll call X minus 8. That 8 comes from 4 -2s equals -3. X equals +5. ClO4 1-, that is Cl, not Ci. Oxygen is -2, so X minus 8 equals -1. X equals +7. Okay, so the question might be, well, so oxygen is on this list back here, and so is chlorine. So why did you have to calculate the chlorine? If you have 2 elements from that list of rules, one of them will be set in stone, the one that's higher up on that list, and the other one you have to calculate. If you made chlorine -1, so let's just go back and say if you made chlorine -1 and oxygen -2, -1 plus -8 would not add up to -1. So If you are given more than 2 elements from that list, you have to set the one that's higher up on that list for whatever it says it is, and then you have to calculate the other one using that little algebra trick. And these, we are actually going to skip these. We don't really cover these, so it's good. All right, so we were going to stop there for the day.